This video I introduce a full PilotNet self-driving model. Earliest PilotNet self-driving model tells us that a simple convolutional neural network can be used to predict the steering angle from input image. Using deep and wide convolutional neural network, full PilotNet self-driving model is able to do line following, lane changing, and turn operations in the real world. First, we use a deep neural network with a stride to extract features from input image. The stride here used to reduce the dimensions of the feature space. And the deep CNN used to extract the important features from input image. However, deep CNN will cause a gradient vanishment problem. That means the gradient travels from the output layer along the neural network. It cannot travel too far and then become to zero. That means at the deep element, we cannot use the gradient to update the model parameters. So to solve this problem, we use residual blocks. Residual blocks are just like a shortcut connection. That means we can make sure this gradient from the output layer travel very far away along the network. So we can use that gradient to update the model parameters anywhere inside the neural network. Another problem caused by a wide convolutional neural network, it means the overfitting problem. To solve the overfitting problem, we use the dropout technique. Dropout, that means during the training time, we turn down some of activations. After we trained the neural network, then we turn off all the activations. Use this way, we can overcome the overfitting problem. Because we use a nonlinear activation, like a ReLU function here. His output has a very large variation. So to stabilize the model training, we use batch normalization to stabilize the model training here. Then let's see the full PilotNet architecture. This is the input image. It's also the observation obtained from the camera mounted on the vehicle. And then we use the 4 residual blocks. That means deep neural network. And then we use 2 more convolutional neural layers. Because these 2 convolution layers is used to further extract the important feature from the input image. We use the residual here because this is located in a deep network. Here, because this is close to the output. So here we don't need to use the residual module. First, we use this 6 convolutional blocks to extract the features from the input image. And then we flatten the 2D feature maps to 1D features. And then we cascade this 1D features with the control inputs together, used as the input of the fully collected layers. And then we predict the output. This is the output layer. For example, this is the speed, acceleration, lane change, turns, and so on. Here is the details about the parameters used in the full PilotNet self-driving model. However, the full PilotNet not put all the control inputs together with the low-dimensional features extracted from the input image. Instead, it just report each control input for one fully collected layers. However, this for each one we have, we just clone this fully collected layers for each control input. That means when we train this model, the model don't need to select the control input. And then we put all the output together as the output of the full PilotNet self-driving model. As we are introduced before, we need to output the silencing mask to show what's important in the input feature for the machine driver. To do so, at each residual block and convolutional layer, for example, this is the last layer. So we have a 2D feature map. And then first we take an average of the feature maps for each layer. And then we use the deconvolution operation to upscale this resolution to the resolution same as his previous layer. And then we pointwise use the pointwise multiplication to calculate the multiplication of this mask layer and this feature maps. This is actually this average the feature map, this feature mask. And then we got the new feature mask, and then we use the deconvolutional operation to upscale to the resolution same as the last average map feature map, and so on until we reach the final feature mask that has the same resolution as the input image. And then we overlay this final feature mask with the input image together to show which part of the input image is important for the machine driver. For more details, please check with this reference. Thank you. Bye.